University, and he'll be talking about polynomial-time Nielsen Thurston type recognition.
Thank you for the invitation. This is joint work with Mark Bell. And throughout, S is an orientable surface. Genus G, and P punctures, which you may, if you wish, think of them as mark points. P could be 0 or positive. For technical reasons, the theorems are really non-trivial when the genus and the punctures are at least some size. And the group that we're interested in is the mapping class group that I'll write mod S. And the hyperbolic space on which it acts that we're interested in is the curve graph of S. I'll mention more about the curve graph later. Before I get there, though, I just wish to motivate a little the main theorems of this talk. And we'll start with the theorem of Thurston. It goes back to the 70s. States the following: let F be a mapping class, then at least one of the following three holds. Either F is periodic, so some non-zero power F to the n is the identity, or F is reducible, or F is pseudo-Anosov. Reducible, let me just clarify what that means. It means there is a collection of simple closed curves, alpha, on the surface S, so that F of alpha is isotopic to alpha. That collection may be more than one curve. And pseudo-Anosov, I'm not going to go into the definition too deeply, but basically it means there are two minimal foliations on the surface, measured minimal foliations on the surface S, so that F locally looks like an Anosov map. It contracts one direction and expands the other. Okay. And in the context of this talk, F being pseudo-Anosov will actually turn out to be the loxodromic isometries on the curve graph. And F reducible or periodic will be ones that have basically zero translation length, coarsely zero translation length on the curve graph. Okay. And here's a follow-up theorem due to Thurston as well. If we write MF for the mapping torus of F, then at least one of the following holds. Either MF admits H2 cross R geometry, or MF has a non-trivial JSJ decomposition, or MF has hyperbolic geometry. And in each of these cases here, correspond respectively to the cases up here. In particular, MF has hyperbolic geometry if and only if F is pseudo-Anosov. Okay, so here's a nice question. If I give you a triangulation of a three-manifold, can you decide, well, how fast can you decide whether MF is hyperbolic or not? That's a pretty hard question. But let's make it a bit easier for ourselves. Let's suppose instead you give me a surface in the mapping class. Can you decide whether the mapping torus is hyperbolic or not? Or can you decide, equivalently, whether f is pseudo-Anosov or not, and how fast can you do it? So that leads us to the following decision problem. What's the setup? Let X be a finite generating set for the mapping class group. Could be a set of Dane twists, for example. And what's the question? Given a word f in X, is f pseudo-Anosov? Okay. I'm going to abbreviate this decision problem by PADP. So here are the following theorems that I wish to discuss in this talk. One, the pseudo-Anosov decision problem is in P. Okay. And secondly, there is a polynomial-time algorithm that accepts a word f and returns sigma f, which is the canonical curve system for the mapping class f. And this is related to the non-trivial JSD composition in the case where f is infinite order and reducible.
So the first statement is polynomial in the length of the word?
Yes. Yeah. Okay. And these theorems will be proved by the following key theorem. Which will make use of the mapping class on the curve graph. Mapping class group on the curve graph. There is a polynomial-time. First of all, I want to fix the surface S. There's a polynomial-time algorithm that accepts vertices alpha and beta of the curve graph and returns a tight geodesic between alpha and beta. Okay? So in particular, you get a geodesic and you get the distance between alpha and beta in the curve graph.
But again, polynomial-time in what?
I will say later. So the truth is that we'll encode alpha and beta in terms of a triangulation of the surface and record how the curves intersect each arc of the triangulation in the bit size of the intersection, and that determines alpha and beta, and that will be the computational framework, and I'll discuss that later. So note that Margalit Strenner and Yurtash also get theorems 1 and 2 via different methods. They do it from a. They don't do this theorem. They use different methods entirely, and they also get the dilatation of the pseudo-Anosov, whereas we get the asymptotic translation length of the pseudo-Anosov on the curve graph. These are two different things, but they both measure mixing of a pseudo-Anosov in different ways. Okay. Both groups are also working on the conjugacy problem in mapping class groups. We're trying to show it's in P. Okay. So, before I move on to talk about the curve graph in more detail, I just wish to acknowledge some work that people have made on these problems. So, in the 80s, I believe Mosher showed that the pseudo-Anosov decision problem could be solved in exponential time. And in the 90s, Hamidi Tehrani and Chen also gave an exponential time algorithm. And both of these approaches use PML and train tracks and dividing polar topes into smaller bits. Also in the 90s, Besvin and Handel described their train track algorithm. And I believe this is exponential time in the word length of the in the mapping class group case. In the case of the braid groups have extra structure that we're sure of, namely the Garside structure. And the relationship between the reducibility of a braid and the Garside structure was described by Benedette, Gutierrez, and Itetsky in the 90s, and later developed by a few people, which I'll write the names down. And all of this work culminated in Matteo Calvez showing that the pseudo-Anosov decision problem is in P for a fixed braid group. And this was done like in, I think, 2011 or so. And it uses the linear bounded conjugated problem property for mapping class groups. And that uses curve graph machinery. So for the braid groups, there has already been some success. But the Garside structure is not known to exist for when the genus is greater than 0. So what are we left with? Well, more recently, Koberda, Mangerhas, and Bell showed that the decision problem is in co-NP. Okay? So if a decision problem is in co-NP, it means that there's a polynomial time proof that the answer is no. So so the answer being no means that the mapping class is reducible. Having a polynomial time proof of that would amount to showing that the canonical reducing curve system has polynomial size. And that's exactly what they do. And later, Bell showed that it's in NP. i.e., there's a polynomial time proof that the mapping class is pseudo-Anosov, and that is harder. He shows that given the measured lamination, invariant measured lamination, Bell shows that you can get the Agel splitting sequence, and then that proves that it's Pseudo-Anosov. Okay. What about the curve graph distance algorithms, or geodesic finding algorithms? In fact, there are quite a few. In 2002, Jason Leisure gave an algorithm for closed surfaces, and later Shackleton gave one for general surfaces. I myself did as well, Yosuke Watanabe, and Berman, Margalit Manasco gave a very simple one for closed surfaces. But surprisingly, none of these papers have an explicit running time on the algorithms. And I suspect that for a couple of these authors, there are no explicit running times because they're quite complicated. So in fact, sort of around this time and before that, my opinion at least was that there was no way it would be polynomial time, that there is a distance algorithm.
What about just the word problem in the mapping class group? When was that known that it's in polynomial time?
I think that Moshe showing that as automatic.
Yeah.
Could you, whether it was before Moshe, I'm not sure. Whether you really need automaticity to decide that. Okay. Okay, so I will define the curve graph and say some nice facts about it now. And then I'll tell you why the key theorem implies theorems 1 and 2. So this definition is more or less due to Harvey, who defined the curve complex. The curve graph is the one skeleton of the curve complex. And what is it? Well, it's a graph, and the vertices are isotopy classes of essential simple closed curves. On the surface. And what does essential mean? Well, it basically just means they're not null homotopic. And they're not homotopic into a puncture. So they're sort of like Z splittings of the surface. Let's look at some examples. Well, this curve is null homotopic, so that's not going to be good. That's not a vertex. This one is not a vertex either. But something which is non-trivial is going to be a vertex. What about the edges? The edges of the graph span two non-equal vertices if alpha and beta can be realized disjointly on the surface. So for example, these two vertices will be adjacent but these two won't be. Okay. Okay, so we can endow the curved graph with the metric by sending each edge length, well, by saying that every edge will have length 1. Okay? And then we have the following facts. Well, first of all, the mapping class group acts on the curved graph by isometries. Even better, it acts acylindrically, which is a theorem of Bowditch. The curved graph is connected. That's reassuring. And it's a locally infinite graph.
Not so reassuring.
Indeed. So it really is a theorem that there is an algorithm to compute distance. Okay, so less trivial is the fact that the curved graph has infinite diameter. So I believe Lila communicated a proof to Maser-Minsky. And Maser-Minsky proved this theorem by showing that pseudo-Anosovs act loxodromically. The curved graphs are hyperbolic. So there's a delta depending on surface. So that the curved graph is delta hyperbolic. Also due to Maser-Minsky. I'm going to abbreviate Maser-Minsky as MM because I will write their names quite a few times during this talk. In fact, we know that delta doesn't depend on the surface now, which is due to Algab, Bowditch, Clay, Rafi, Schleimer, Hensel, Shatitsky, and myself. And yeah, I will say some more interesting facts about it later. But I think for now, I want to talk about how the key theorem implies theorems 1 and 2. So specifically, I'll give a sketch of why it implies theorem 1. It also implies theorem 2, but I won't explain that in more detail. So I'll need the following notion, which is that of the asymptotic translation length, or stable length. So let F be a mapping class. And the asymptotic translation length of F is the following. The following real number. You take a limit as n tends to infinity of 1 over n times the distance between gamma and the nth iterate of f acting on gamma, where gamma is fixed. Gamma is a fixed vertex of the curve graph, and in fact the choice will be independent. Okay. And what's so nice about the asymptotic translation length of f is that it detects whether the mapping class is pseudo-Anosov. So here's a nice theorem due to Mazur and Minsky. There is a constant c depending on s, which is positive, such that f pseudo-Anosov implies the asymptotic translation length is at least c, which is positive. What's particularly nice about this theorem is that this c only depends on the surface, not the pseudo-Anosov. So it's a bit stronger than just saying pseudo-Anosov is a positive translation length. Gardner and Tsai gave sharp estimates for c in terms of GMP, sort of polynomial GMP. Before I move on, I just want to say that this asymptotic translation length has a nice property that it's multiplicative under taken powers. Okay. Feel free to ask questions. It's also worth mentioning that if f is either periodic or reducible, then it's actually not hard to show that the asymptotic translation length is 0. Okay.
So the converse of the theorem is not true, right?
Yeah. Yeah, so this is an if and only if because we've exhausted all the possible cases of f. Okay. Right. So, yeah.
Can you get a hold of this norm of f also by choosing a hybridization and looking at how, I don't know, traces of iterates behave? I mean, so using SL2 and matrices.
Oh, so in the case of the Ferry graph, for example, like in the case of SL2Z.
Yeah, but how are you going to do it on higher Jonas surfaces?
I don't know. Yeah, that was my question.
Oh, how are you going to? Okay. Looking at action on homology, for example, or I mean, there are things in the Torelli group that are pseudo-Anosov. Action on the surface itself. Yeah, it's quite difficult to say because you can start exponentially growing automorphisms that are reducible. Yeah, it's interesting. I would love to see some really nice different definition of this. I would like to see that.
Pseudo-Anosov comes with an eigenvalue, right?
Yes.
A real number. So is this related to this number?
Yes, it is related. So I believe that this gives a coarse lower bound on the dilatation. Okay, thanks. Okay, so.
You have an example where this thing is not an algebraic integer? Or?
Oh, well, actually, it's a really nice theorem. It is an algebraic integer in a really silly way. So Brian Bowditch, he has a paper where he proves that the action is acylindrical, but he also shows that there is a constant m depending on s, so that this guy always is a rational number with denominator they're uniformly rational, so the denominator is a multiple of m, I think. I might be getting confused. They're uniformly rational. So, you've got lots and lots of rationals. Their denominators can get arbitrarily big. But Bowditch says along the line they must lie in z times 1 over m.
Oh.
Yeah, so that's a better way of putting
Better
it.
than being an algebraic integer.
Yeah.
Screen.
Yeah.
So this is a good theorem that in fact allows us to compute what this thing is by approximating it. Okay, so I can tell you the procedure for how this algorithm is going to work to determine whether you're pseudo-Anosov or not. So what's the setup? I'll get into the nitty-gritty later, but I'll just say what the overall setup is. You've got your surface S and it's fixed, and gamma is a fixed curve on the surface. And then you're given mapping class F, and I'll tell you what to do. So we pick a large uniform constant n, capital N, and it depends on the hyperbolicity of the curve graph. It depends on this constant c over there. It depends on the bounded geodesic emission. Don't worry about that. And then we do the following. So we compute a geodesic G from gamma, this fixed curve, to f to the n gamma using the polynomial-time geodesic finding algorithm. Okay, and then shout if you can't see this. And then we take a midpoint, gamma prime of the geodesic G, and then we look at how f to the n translates gamma prime, and then we'll say that that's going to approximate the translation length of f to the n. So number 3, we compute the distance between gamma prime and f to the n of gamma prime, and then let's call this d for short. Then if d is large, in a sense that will be clearer later on, then f is pseudo-Anosov. And if d is small, then f is reducible. I've ignored the case when f is periodic, because that's already known. To determine whether f is periodic or not, that's already known to be in polynomial time. Okay. So that's the procedure. Why does it work? Well, let's draw a picture. Here's the curve graph, and we're given some we fixed gamma once and for all. And then you give me some mapping class. Let's look at the case analysis. Let's suppose f is pseudo-Anosov. What happens? Well, we know that f is loxodromic thanks to Mazur and Minsky. So there is some sort of quasi-axis on which f acts by translation. Okay? And we also know by Mazur and Minsky that the asymptotic translation length of f is at least c. We've raised f by some large power, and therefore the asymptotic translation length of f to the m is at least nc, and that could be large, okay? Because we choose n, capital N to be big enough. We just need proof that it's large now, okay? So how we do that? Well, when f translates this axis, it translates gamma as well. But also this is going to be coarsely at least nc, and this could be at least 8 delta, or how much you need it to be, something like 16 delta. And so the geodesic G fellow travels the quasi-axis for f. And you can show that gamma prime, the midpoint that we take in the procedure, is going to be within 2 delta of this quasi-axis. And therefore, when you calculate this distance gamma prime f to the n gamma prime, well, it's going to be approximating the translation length of f to the n. So in particular, since this is large, this will be large. And that's good. We only need to check the case where f is reducible. So in the case where f is reducible and has infinite order, there is something called the canonical curve system. Of f, and f acts on the complementary subsurfaces of this curve system by either periodics or pseudo-Anosovs, or it might twist along the curves in the curve system as well after taking the power. And f acts on the curve graph sort of like rotations around the canonical curve system. And if you take a large enough power of f, then a similar sort of phenomenon happens as in Damoni's talk, where the geodesic must go through or very close to the canonical curve system. I'm not going to explain the details of why that's true, but it's something called the bounded geodesic image theorem due to Mazur and Minsky. G must come close to sigma f. Okay, so the picture will be this. Okay, so here's G. and let me pick a different color. It turns out that you can prove that gamma prime, the midpoint, a midpoint, is within 2 of some curve in the canonical curve system. So if you cook up this capital N in the correct way, then you can show that the distance between gamma prime and f to the n gamma prime is at most 4, which is small. Okay? So that's the end of how the key theorem implies theorem 1. Okay, so the rest of the talk will be about talking about the key theorem and how to prove it. Let's first be very careful and tell you what the setup is. So what we do in the case where S is punctured, is we fix an ideal triangulation curly T of S. Okay, so for example, you can take the genus 2 surface, puncture it once, and then triangulate it. That'll give you an ideal triangulation of S21. And I said that you give me alpha and beta, and I have to find geodesic between them in the curve graph. The way you give me alpha and beta is you tell me certain weights of how many intervals you see on the surface. So in general, if you have edges EI, the triangulation, you tell me the numbers of how much alpha intersects each edge of EI of T. And these numbers determine exactly the curves alpha and beta. And these are given to me in bits. So when I say polynomial time, I mean it's polynomial in the bit size. Of these intersection numbers. Okay. If you have any questions, just ask and I'll make it clearer.
Just mean the logarithm of that.
Oh, sorry?
Just mean the logarithm of.
Yeah, so it's just the logarithm of these guys. If we had polynomial in the intersection, which is a priori exponentially bigger, it wouldn't be enough to show that the Pseudonov decision problem is in P, because you have exponentially growing mapping classes, and so this thing grows exponentially. So the fact that it's polynomial time in the bit size is necessary for the application. I didn't tell you what we do when the surface is closed. Well, if it's closed, then you add a virtual marked point. So it complicates the discussion, unfortunately, because the representative of alpha here is unique. But in the closed case, you have point pushing maps past the virtual puncher. So it's a bit more complicated, but you can still do it. Okay, so I'm going to now give an overview of the algorithm. So it comes in 3 steps, and I might need more colors. There was a blue around here somewhere. Okay, so here's the curve complex, curve graph, and here's alpha, and here's beta, and we have no idea where they are or how far they are apart. And, well, how are we going to get geodesic? Well, the first thing we do is compute a reparametrized quasi-geodesic from alpha to beta. So there's a constant depending, I think the constant's independent of anything. If we compute a k unparameterized quasi-geodesic from alpha to beta, and what's that? It just basically means it's a quasi-geodesic that doesn't backtrack, essentially. Okay. The only thing we need is that this set is quasi-convex, actually. That's all we really need. Not very much room to write, so I'll move to this board. Step 2, we compute these little paths between each red vertex in this cloud. Okay, and the paths that we compute, we'll just call them type paths. So we compute all the type paths of length at most L, where L is just a universal constant, between each red pair of vertices. So these guys are red, and now we compute all these type paths. Okay. And now there's a theorem that states that all tight geodesics between alpha and beta are contained in this set. Tight geodesics are a special class of geodesics in the curve graph, which were introduced by Mason and Minsky, and they have local finiteness properties. So this set is finite now and contains a geodesic. So what we do now for step 3 is we use any polynomial time geodesic finding algorithm for finite graphs, such as Dijkstra's algorithm, to find a geodesic, any geodesic. So since there is a tight geodesic in that set, there is a geodesic in that set, and we can find it using Dijkstra's algorithm. So that's essentially the overview of how this algorithm works. I suppose I could say a couple of words about either step 1 or step 2. I'll give a hint to what step 1 involves. So, step 1, we use some work of Egel, Haas, and Thurston to compute fast train track splitting sequences and Mazur-Minsky showed that these provide k-unparameterized quasi-geodesics in the curve graph. So that's essentially what's involved in step 1. I'm not going to give any more detail than that. And step 2, I'll just define type path briefly, what type paths are, and then I'll stop. So, definition, a type path gamma 0, gamma 1, dot, 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 is a sequence of multi-curves on the surface such that the two following things hold. So 1, for technical reasons I want n to be at least 3. Whenever I and j are indices and they're at least 3 apart, then gamma I and gamma j fill the surface. And lastly, gamma I is always obtained by taking gamma I minus 1 and gamma I plus 1, uniting them, taking a regular neighborhood and then take the boundary and keep the essential curves. Okay. So I think I'll stop there.
Does anyone have any questions? At the back.
So for step 1, when you say compute a k-unparameterized quasi-geodesic, so you need to do it in polynomial time, and that's what you're saying that Egel, Haas, Thurston allows you to do?
Yeah, because a priori there could be very large Dane twists hidden in amongst this region, and if you just do train track splitting sequences, they could be exponentially long.
But if you block those out, then it's...
Yeah. So Egel, Haas, Thurston tell you how to get through the Dane twists very quickly and get polynomial time.
Anyone else? Okay, let's thank our speaker again.